Today I'll be telling you about a connection between the maximum matching problem in dynamic graphs and the Ruzsa-Szemerédi problem, a notorious open problem in combinatorics. By the end of the talk, I'll sketch how, if you can make progress on the self-contained combinatorial problem, you will automatically obtain a faster algorithm for one of the most fundamental dynamic graph problems. In the dynamic maximum matching problem, we start with an n-vertex graph G. At each time step, an edge is either inserted or deleted, and along the way, we must maintain a matching of maximum cardinality. We'll be interested in minimizing the worst-case amortized update time of our algorithm. The current fastest algorithm for this problem is due to Sankowski and has update time n to the 1.49. We'll actually focus on the approximation version of this problem, where we are only required to maintain a matching of size 1 minus epsilon times the size of the current maximum matching. We can solve this relaxed problem much faster than we know how to solve the exact version. For instance, a result of Gupta and Peng shows that for any fixed epsilon greater than 0, there exists an algorithm with an update time that is linear in n. Of course, this problem should become easier as epsilon increases. Indeed, a result of Bernstein and Stein gives an algorithm which runs in just square root n update time for epsilon greater than 1/3. And if we increase epsilon all the way up to 1/2, then a result of Baswana, Gupta, and Sen gives a dramatic improvement to just log n update time. These results raise the following major open problem. Could it be the case that for any epsilon greater than 0, there exists an algorithm with an update time n to the little o of 1. As a small note, throughout this talk, I will suppress the dependence of epsilon in the asymptotic notation. If this bothers you, feel free to think of epsilon being 0.01 for the rest of the talk. This brings us to the recent work of Asadi, Khanna, and Kiss, which refined prior work of Benazad and Ghaffari. They gave an algorithm with runtime n to the little o of 1 times some function, ORS, of n, epsilon times n. For the time being, it's not important to know what ORS is. We'll come to that shortly. What is important to know is that the best upper and lower bounds we have on ORS are extremely far apart. The best upper bound is just barely sublinear, and the best lower bound we have is n to the big omega of 1 over log n. And there are some reasons to believe that the lower bound might be closer to the truth. If this is indeed the case, then this algorithm would give an affirmative answer to the problem of the previous slide. These papers asked whether we can replace ORS, which was first defined by Benazad and Ghaffari, by another function, RS, which has been extensively studied since the 70s in combinatorics. In the rest of this talk, I'll tell you about my result, which is that this is indeed possible. The main objects of interest in this talk are Ruzsa-Szemerédi graphs. We say that a graph G is an R, T Ruzsa-Szemerédi graph, or RS graph, if its edge set can be partitioned into T matchings of size R, where each matching is in fact an induced matching in G. As a simple example, the 6th cycle is a 2, 3 RS graph, since we can partition its edge set into 3 induced matchings, each of size 2. A major open problem in combinatorics, first investigated by Brown, Erdős, and Sosch in 1973, is to determine for which values of R and T there exist RT-RS graphs on n vertices. Specifically, they asked if both R and T could be close to their trivial upper bounds of n. For instance, could they both be linear in n? Such a graph would be somewhat surprising, as the subgraph induced by any given matching is very sparse, with just a linear number of edges, since it's a matching. Yet somehow, these matchings have to overlap in such a way that the entire graph is dense, with nearly n squared edges. We'll let Rs of n, R be the maximum T, such that there exists an n-vertex Rs R, T graph. So the previous question is the same as asking if Rs of n, big omega of n is at least big omega of n. This problem was resolved by Ruzsa and Szemerédi, who showed that in fact Rs of n, epsilon n is at most little o of n. But they also showed that, perhaps more surprisingly, Rs of n comma r is linear in n when r is some slightly sublinear function of n. Their work, however, left open the problem of determining Rs of n comma epsilon n, where epsilon is less than, say, 1/5. This problem remains wide open, with the best lower bound being n to the big omega of 1 over log n, and that's due to Fisher, Lehman, Newman, Rashodnikova, Rubenfeld, and Samornitsky, and the best upper bound being n divided by log n, iterated big O of log of 1 over epsilon many times, and that's due to Fox. We now define a variant of RS graphs introduced by Benazad and Ghaffari in the context of dynamic matching. We'll call a graph an R, T ORS graph if, as before, its edge set can be partitioned into T matchings, each of size R. But now we will only require that the ith matching, M sub I, is an induced matching in the graph that is the union of the first I matchings. Note that this is a weaker condition than before, so any RS graph is also an ORS graph. For example, here is a decomposition of a graph with the ORS property, but not the RS property. Here I've labeled each edge by the index of the matching to which it belongs. If we look at the subgraph induced by M1, for instance, we have a matching. Similarly, M2 is an induced matching in the union of M1 and M2, and M3 is an induced matching in M1 union M2 union M3. However, the subgraph induced by M1 in the entirety of G is not a matching. As before, we define ORS of n comma r to be the maximum T such that there exists an n-vertex R comma T ORS graph. The best known bounds on ORS are very similar to those that we have for RS. The best known lower bound is the previously mentioned construction of RS graphs due to Fisher et al., and the best upper bound is n divided by log n, iterated polynomial in 1 over epsilon many times, and is due to Benazad and Ghaffari. Because ORS is a relaxation of RS, it's clear that RS is at most ORS. But recall that our goal is to replace ORS by RS in the runtime of the algorithm of Asadi, Khanna, and Kiss. So we'd want the reverse inequality to hold. However, we really only need to rule out the possibility that RS could be significantly smaller than ORS. For instance, could it be the case that ORS grows as some polynomial function of n, but at the same time, RS is smaller than any polynomial function of n? We'll show that the answer to this is no. Specifically, we'll show that if ORS of n comma epsilon n is at least big omega of n to the c, then for any delta greater than 0, RS of n comma big theta of epsilon n is at least big omega of n to the c times 1 minus delta. So if one of RS or ORS grows as some polynomial function of n, then so does the other, with essentially the same exponent. This result follows quickly from the following lemma. For any n, k, and r, RS of n to the k, comma r to the k, is at least ORS of n, comma r to the k minus 1 divided by k. To see why this implies the previous claim, suppose that ORS of n, comma epsilon n is at least n to the c. Then taking r equal to epsilon times n, we conclude that RS of n to the k, epsilon n to the k, is at least n to the c times k minus 1 divided by k. If we then choose k to be 1 over delta, we conclude that RS of capital N, epsilon to the 1 over delta times capital N, is at least n to the c times 1 minus delta for all capital N, which are kth powers. Values of capital N, which are not kth powers, can easily be handled from here. Now let's prove this lemma. Suppose that G is an n-vertex ORS of R, T graph. We first take the kth tensor power of G. recall that this is the graph whose vertices are k tuples of vertices in G, and two such tuples are adjacent in G tensor K, when each coordinate is adjacent in G. Next, we define G tensor K sub S, which I'll just call our big graph. This will be a subgraph of G tensor K. It will consist of those edges u comma v in G to the K, where the sum over each of the K coordinates of the index of the matching to which edge ui vi belongs in G is equal to S. Here I define f of ui comma vi as the index of the matching to which edge ui comma vi belongs in G. Now, given a vector of length k with entries in 1 through t, which is just the number of matchings in G, recall, we define a subset of edges in the big graph as follows. M sub a will be those edges for which f of ui comma vi is equal to ai. So it's the set of edges in our big graph whose first coordinates are adjacent in matching a1 in G, whose second coordinates are adjacent in a2 in G, etc. The key claim is that MA is an induced matching in the big graph. Note also that every edge in the big graph belongs to a unique set of the form MA for some value of A, and hence we will have a partition of the edges in the big graph into induced matchings. We first claim that MA is a matching in the big graph. To see this, suppose that we have three vertices u, v, and w in MA that violate the property of being a matching. So say u is adjacent to v, u is adjacent to w, and v is not equal to w. Because v is not equal to w, there exists some index I for which vi is not equal to wi. Also, we have that ui is adjacent to vi, and ui is adjacent to wi. But by definition of MA, we know that ui, vi, and wi all belong to matching M sub ai in G, which is, well, a matching. So we've reached a contradiction, and so MA must be a matching. To see that MA is actually an induced matching, suppose that two vertices, u and v, are adjacent in the subgraph of the big graph that it induces. The ORS property now comes in. Because G is ORS, it must be the case that f of ui vi is at most ai, as the subgraph of G induced by matching ai can only include edges of matchings of index less than ai. Moreover, the sum of f of ui comma vi over all coordinates I is equal to S by design, and this is also just equal to the sum of all the AIs, of course. So we have a bunch of non-negative numbers that are all at most AI, and whose sum is equal to the sum of the AIs. And so we conclude that f of ui comma vi is actually equal to ai for all I. But this implies the edge u comma v belongs to MA by definition. Since we previously showed that MA is a matching, we conclude that MA is in fact an induced matching in the big graph. Putting everything together, the number of vertices in the big graph is equal to n to the k. The size of matching MA is equal to r to the k, as for each coordinate I, there are r edges in the matching M sub ai to choose from. The number of matchings is equal to the number of vectors of length k, whose coordinates sum to s. By the pigeonhole principle, this is at least t to the k over k times t, for some choice of s. This shows that Rs of n to the k r to the k is at least t to the k minus 1 divided by k. By choosing t to be maximal, we conclude the proof of the lemma. We can now drop this bound on ORS in terms of Rs into the result of Asadi, Khanna, and Kiss, and conclude that there exists an algorithm for the 1 minus epsilon approximate maximum matching problem with update time n to the little o of 1 times Rs of n comma epsilon n. The obvious open problem is to determine Rs of n comma epsilon n, which will either lead to a significantly faster algorithm for the dynamic matching problem, or it will yield a lower bound construction which has evaded combinatorics for decades.